It is the March 5th lecture. Happy Cinco de Mayo. Okay, here we go. So I have two tasks today. One is to make you think, two is to make you think, and three is to answer a quiz question. Let's see if we can do them all together. Make you think about thinking, make you think, and answer the quiz question. I am 6 inches taller than my son. My son's friend is an inch taller than he is. How much taller am I than my son's friend? 5 inches. How'd you do that? How'd you know to subtract? Right? Did you need an equation that you memorize? If A is 1 foot greater, whatever, then blah, 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 blah. No, you just visualize it. You visualize it. Here's how I think of it. I picture, here's me. Here's Nalo, my son. He's the son. Here's his friend Simon. I picture myself being, what did I say first? I said I'm 6 inches taller, right? And then Simon is an inch taller than he is, right? So Simon is a little bit bigger than the short dude. Just kidding. Simon is like a foot taller than him. It's really cute. They're the same age. Simon's giant. Nalo is microscopic. So this is 1 inch. I don't like that. I don't like that. I don't like that. Go away. That's 6 inches. 1 foot. No. So what's the difference? I've got 6 inches down and 1 inch up. 5 inches difference. Another silly example. I gave Nalo $5. Nalo pays the bills, by the way. Nalo gave Simon the electricity bill, which was $5. What's Nalo? What's my net worth compared to Simon's net worth? Again, think about it. I gave my son a $5, not the bunny from Watership Down, $5 bill. I saw my son give the electricity bill, which he is, of course, responsible for paying at age 9, 8 and 5/10, whatever. Gave Simon a bill for $5. Now Nalo doesn't have to pay it. How much richer am I than Simon? Google for him. I gave Nalo $5. Nalo gave Simon a bill. How much richer am I than Simon? This is Google form B. B, right? B? Yeah, B. B. You can and should discuss with your neighbor, by the way. Putting it into words, putting it out loud will help. All right, let's see what you put. Time's up. How much richer am I than Simon? Oof. No, you guys don't like money. I know your generation doesn't have any practice with money. Doesn't have any experience of it. $5 is what, a week's worth of wages for your generation, it's just screwed even more than mine. Okay. So I'm on your side, by the way, with that. Okay, point is. How much did I lose? I'm $5 less than I was before, right? How much did Simon get? He got a bill, damn it. Now he's got to pay $5. How did his wealth change?
Bill is like a bill, not like a...
Yeah, he's paying the electric bill now. Simon's got to pay the electric bill instead of Nalo. Oh, really? Oh, you thought like a dollar bill? Oh, oh no. The electric statement, my APS debt. There we go. $5 debt. I'm sorry. Okay, fine. Now it's going to be William and Billard for the next people. Okay, no, so this. Hey, change your answer. Change your answer if you wish. Answer B, you can edit your response and change it. My son has given Simon $5 of debt. I give my son $5. My son, who normally pays the electric bill, pays the electric debt, gives it to his friend Simon instead. Now Simon has to pay. Compare my wealth with Simon's wealth. How rich am I compared to him? Assuming that we all started out equals. All right, let's see what you put. Better. Good. They're equal. I lost $5, giving it to Nalo. Simon lost $5. He's now paying a bill. He's got a debt. So assuming all of the things being equal, assuming we started from an equal point, which is stupid with money, right? That's never true. We're both in debt by $5. We're equals. Another example. I love ham radio camping trips. And we established 3 camps. There's the student camping area. Let's keep it simple. There's the camping area. There's the meals/socialization area. And there's the station itself, the radio station. Gesundheit. Okay, so three places, 3 locations, three tents, if you will. Sleeping, eating, sleepinging. Oh my God. Oh my God. I need a break. Eating tent, mess tent. They're all messy. And radioing, the most important, of course. We carry crates of stuff up and down a lot, right? And inevitably, the packing lists are never what they should be. So we're carrying stuff back and forth and back and forth from this place to that place to the other place. And I'm going to tell you, it takes 25 joules to go from sleeping to E. You can get 10 joules letting a box, I should say a box, takes 25 joules to get a box. That's ungrammatical, but whatever. Go from radios to eating. Where is radioing compared to sleeping? What's my hike when I wake up in the middle of the night to take my shift? This is question 1 that gave most of you heartache on quiz 6. Put your test in, put your answer in question C, right? Where is how much energy? How much energy does it cost to go from R to S? Yeah, R to S. Actually, I said it backwards, didn't I? I end my shift and then I go to conk out on my tent. So how much energy does it cost to go from the radio station to the sleeping bags, tents, whatever? Take it one piece at a time. Draw a picture. It isn't this hard. Once it clicks, you push for it, you'll never have trouble with this stuff again because your brain has grown. Push for it. Push for it. You can do it. No, hold on. The second story, the latest story I told is incorrect. If I'm asking where are the radios compared to the sleeping area, I'm not saying I go from the radios to the sleeping area. I'm saying if I'm at the sleeping area, am I looking up or down and how much? Where are the radios compared to the sleeping area? The sleeping area is my initial. Final minus initial, right? So I'm not at the radio station. If I'm comparing it to S, I'm saying I'm at S, where is R? All right, here's how I reason. Wait, do you want another minute? Are you still thinking? I still see people thinking. Great, keep going. Okay, let's think this through as a class. Step one, it takes 25 joules to go from sleeping to eating. Which one's higher? If it takes energy to go from the sleeping tents to the mess hall, which way's up? It takes me energy to go eat. E is above S. How much above S? That's a 25 joule cost to drag my, oh, radio up. Okay, now at the radio station, if I go from radio station to the eating, to the mess hall again, how has my energy changed? I can get energy. I can, I don't know, make the radio move, give it some kinetic energy by dropping it and letting it speed up. Is radio station higher or is mess hall higher? If I get energy out of it, gravitational potential energy out, I think the radio station has to be the higher point. How much higher? At the end of the day, I ask, where is R compared to S? I'm at S. Where's R? 35 joules above. Positive 35 joules. You get that right? Let's take another look at the quiz problem. Take another look at the quiz problem. The numbers were randomly generated. So let me make them up. It takes 5 joules to bring I'll just kill the SI units, from A to B, and you release, or you can get, or you have negative cost, can't double count. You release 7 joules going from B to C to B. I forget how I exactly worded it. What's the voltage at C relative to A? You guys know WRT, with respect to? WRT means with respect to. This is question, what are we on? D. Give it another try. Draw a picture. Yes, Abby. If it takes energy, I have to do work pushing it in. If it takes energy to move something from one point to another, I am giving it energy. Potential energy is upping, increasing. Voltage is increasing if it's a positive charge. If energy is released from one point to another, that potential energy is going down. You are going downhill energy-wise. Question or thinking? Someone said Tucker. Yes, please meditate, Ryan. Meditate and gain enlightenment. Physics enlightenment. Oh, A, you get an A? Nerd. Hold on. Yeah, question. 2 coulombs worth of charge. If I have a number and a letter, that letter means a unit. Wait, hold on. Somebody else asked a question in chat. By the way, that means the people in chat are online are listening. I love you. Thank you. Bringing the energy would be negative. Wait, bringing? I didn't say bringing. Did I say bringing? Ooh. I mean bringing. Say that again. Question. That's what I was just talking about. Good. Okay, so yes, again, if it takes energy, then the potential energy is going up. I am doing work on something. I am exerting an oomph. Whereas putting energy in, potential energy is going up. Whereas if energy is released, energy is going down. Potential energy is being transformed into kinetic energy. Question about, say, bring 2 coulombs. Oh, I did say bring in this. To bring 2 coulombs, to push 2 coulombs. The 2 coulombs is the charge. And I am moving it, bringing it, taking it, transferring its location from A to B, and then from C to B, doing these various tests. Okay. Like half the year done with D, but keep thinking. Keep wrestling with it. Okay. I'm making a recording. So watch it. And very important thing about recordings, pause every time I ask a question and do the darn thing. You won't get participation, actually you probably will, depending on how early you leave. You don't have to do every participation question to get participation points. Participation points aren't the point. The learning only happens if you don't watch somebody else think. You have to try it yourself. So pause it, pause it, pause it, pause it, pause it. Good. All right. Looks like a bunch of people are done. Other people are stuck. Here we go. If you're stuck, here's how I reason about this. If it takes me 5 joules to go from A to B, is A or B higher? B's higher. I am pushing something where it don't want to be. I am B. I am storing energy in it, getting it from A to B. B is higher. How much higher? 5 joules of energy higher. So if this is A's energy level, B's energy level is up here. I've gone up by 5 joules. If it takes energy to bring a positive charge from A to B, what's the voltage from A to B? 2.5 volts. 2.5 volts from A to B. B is 2.5 volts higher, 5 joules higher than A. We can't do this without interpreting the pieces. Does that feel okay? Why wouldn't it be negative? Why wouldn't which one be negative? Ah, you're thinking about yourself. Oh, so selfish. You're thinking about the energy that you are expending. But when we're talking about potential energy of the charge, we don't care about you. We care about how much energy does the charge have. If I am using up my energy, I'm giving it energy, potential energy. Very good question. Did y'all hear K Money's question? K Money asked, why isn't it a negative energy if I'm expending that, doing that work, losing energy? Because that's about me. And the voltage isn't how much energy do you exert getting a particle there. It's how much does it have by dint of being there. Think about the particle. What does the particle get? It's all about the particle. Very good. I think there was another hand somewhere. Yeah. Joules per coulomb is voltage. Definitional. Now C to B, if I've released energy, which is higher? I have taken a electrical potential energy and transformed it into, I don't know, kinetic energy. It speeds up as it rolls downhill. It's rolling downhill, C is higher. How much higher? Well, let's say I could say, I have gone downhill, releasing 7 joules of energy. B is -7 above. I have released 7.5 joules, which is to say -3.5 volts with respect to B from C to B. But look, the magnitudes here, B is 2.5 volts above, B is 3.5 volts below C. That's the 3 plus 2 is 6 volts above. C is 6 volts higher than. And if I asked, I could actually write this as an arrow. What is C compared to A? To go from A to C, initial to final, I've got to go up by 6. Okay, turn to your neighbor and express this. How do you do these? How do you think about these? Put it out in your own words. 2 minutes. In what way? Adding or subtracting? How do you know to add? You cannot guess whether to add or subtract and which to add or which to subtract. No, you will screw up half the time. Half the time you get lucky. I would do that and test that.
So, like you were saying earlier about the battery, that's why it's -7 on this one, but on this one, it's 80.
Say that again?
Like, the -7 joules C in relation to A is above it, so
What I drew is as I go from C to B, I have lost 7 joules. 7 joules are released from electrical form. -7 joules above. So what's this difference? C is above B by how much? 7 joules worth. Now, yes, in this case, you can add 5 to 7 and then divide by 2. But how do you know to add 5 to 7? Sometimes it's adding, sometimes it's subtracting, sometimes it's subtracting one from the other, sometimes it's subtracting the other from the one. Yes, if you just guess, you got a 1/3 chance of getting it right. Question. Well, is B higher than A? How much? Is C higher than B? By how much? 3.5 units. How high is C compared to A? Yeah, I could have totally switched this around. If I said it takes 7 joules to get from C to B, that would have put C below A. Then I'd subtract, say 5 minus 7. Okie dokie pokey pony. I challenge you to practice this. I give, did I put this on the homework? I can neither confirm nor deny that there is one problem like this on the midterm. This is a core example, though, of just what I was talking about in my before lecture motivational / throwing down the gauntlet speech, which is to say, you don't memorize equations here. It's a reasoning thing. It's a logic thing. This is what grows your brain. Don't do Sudoku. Learn by thinking about it. Okay. But now is time. Now is the time for me to break your brains in a different way. Or stretch your brains. Hopefully stretch, not break, stretch. I'm going to play with capacitors a little bit. This involves knowing the core equations for capacitors. I'm going to give you 30 seconds to look through your notes and review the core central equations. Know where that is in your notes at the least, preferably memorize real fast. The core equations of electricity, and in particular, capacitor equations. Real fast, review, have them on your paper. Know where they are. Capacitors, central equations. What? No, it's a bunch of equations. But I want you to think 2 seconds. Preload your brain. Time's up. Now we're going to apply this. We're going to use this. We're going to use what hopefully you just were thinking about. And we're going to find an expression for the density of energy inside a capacitor. And it's going to turn out to be kind of cray-cray. I'm going to give you a capacitor. Merry Christmas. Here's a capacitor. No, not literally. Here's a capacitor. It's got sides, I don't know, length by width, and they're separated by a distance d. And the last class I gave them voltage. I'm going to say put Q charge on the capacitor. What question are we on? Google form. Let's start easy and get hard. E, what is the volume of the capacitor? F, what's energy stored in capacitor? G, express F, express capacitor energy in terms of E. This is not an equation I gave you. You're going to have to combine 2 algebraic equations. What's E mean? Electric field, not energy. H, find energy per volume, where you're expressing it in terms of electric field. Should work with each other, remind each other of the equations that the other one has forgotten, help each other out. Yes, it's a couple of steps of algebra. If you've got the core equations, though, it's just manipulation. Uh-huh. Not hell out. What's the volume of a cube? Not cube. Rectangle. Ooh, that doesn't sound good. You sick? You a sicko? Sorry. Ugh. Sorry. Sucks. My baby sounds like a smoker right now. I don't think he smokes. I don't think he's got a Marlboro in his crib. It's been back to back for many months. This, that, and the other. Sometimes getting us sick too. Teaches as well, especially public school. Especially like university, not so much, but they have really strong immune systems. They'll outlast the apocalypse. Elementary school teachers. What's volume? About 85 decibels, eh? Length, width, depth. What is the energy equation that we just spent all class on last time on? Cough, cough. Now V, we don't have V. What do we have? We got Q, we've got the dimensions of the capacitor. Dimensions of the capacitor, what does that make you think of? Knee-jerk reaction. If you've got the size and shape of the capacitor, you've got the capacitance, A epsilon over D, right? So instead of half QV, I could turn V. How do you turn V into capacitance? It's the relationship between V and C. Q equals CV. Yeah, so here, I'm going to write this down bigger. Right? And then C, well, Q squared over, fraction and a fraction, which could be expressed as dq squared, dq, 2a epsilon naught. Here's the energy in terms of what's given. Oh, I didn't give you A, it would be L times W. Whatever, screw it. Ain't nobody got time to write that. So here's the correct answer for F. In terms given, ew, gross, right? dq squared over 2a epsilon naught, who gives a crap? Just wait, just wait. Yeah, energy stored in the capacitor in terms given. How is electric field related to any of this? What's the relationship between electric field and charge on a capacitor? Well, that's important, absolutely. But there's an equation that I gave you for electric field in a capacitor. Yeah, but say this is air dielectric. I don't want to carry around. There's enough variables being carried around right now, right? And remember the electric field and capacitor equation? Charge density, charge per area, divided by epsilon naught is how I remember it. Okay, so can I use this to get rid of Q? Q is A epsilon naught E. Take this and shove it into that equation. Shove it up your Q. What do I get? D A epsilon naught E squared over 2A epsilon naught. Algebra this a little bit. What happens if I square a product? What happens if I divide A squared epsilon naught squared by A epsilon? Pew, 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 pew. You got to make the pew pew noises. It helps the arithmetic work better, the algebra work better. Wait, hold on. This is total energy expressed in terms of C. By the way, this is what I was hoping for. If you got here, big congratulations. This is the answer for G. What's this divided by volume, baby? AD dies. Whoopsie, I dropped a square. Great, who cares? Well, there are two reasons we do this. The big one, the major one, is to force you to revisit the core equations that we've been doing for a couple weeks now. Every single one of the puzzle pieces that went into this is something that you should know. I give you a couple homework problems to motivate you to follow along with this. I think 2 homework problems with this in. Merry Christmas, you've got an equation now. But the vast majority, 90% of why I'm doing this, is to force you to go over those equations and think about how they could be combined. The second way is, whoa, whoa. Okay, epsilon and 2 are constants, duh. But this just gives me a new way to visualize electric field. The square of electric field, square of electric field. Square of electric field is how compact fine energy is. How much oomph there is per volume inside around the capacitor. How densely packed capacitor. This actually applies for any electric field. This is not just capacitors. Anything, any time you have an electric field, there's energy stored in that electric field configuration to the tune of E squared times a constant. This doesn't depend on the capacitor. This is a generic truth about electric fields and the energy that they carry. We'll actually, God willing, we will touch on this at the very end of the semester. We'll see that waves, electromagnetic waves, have an intensity related to their power transfer, and there's magnetic field component and electric field component, and they come together. We may or may not get there. I may shuffle that off to the end. You could deduce, well, whatever. We'll get there, maybe. Okay, so we have come to the time I get you for another 25 minutes. Good. Hey, that's exactly where I hit. That's exactly when I hit this on the 3 o'clock as well. It is now time for capacitor exercises. Capacitor exorcism. Somebody know a priest? My capacitor's got its head spinning around. I think I'm going to give you a different version that I gave the 3 o'clock. You can look at the lecture notes, or for both classes, you could look at their lecture notes to see their challenge. Okay, so here we go. The point of this, by the way, what I'm going to do here is no one does what I'm about to describe. This would be very impractical. I can't think of a real world time that this would happen, but goes back to, this is probably the central, most important, most useful tool in what I was badgering you about before class. You want to understand the what the hell, why the hell these things behave the way they do. You got to think about what they are. You got to visualize them. You got to interpret them, not just have alphabet soup of equations. The equations are important. The equations are, I think, the easier way to describe some of these relationships. But many of the others are, you got to think about, what does it mean? What does it mean? What does it mean? Okay, so I give you a capacitor. He hooks to battery. And then, and here's something that I never do, I'm going to come in, grab the plates of the capacitor, and squeeze them together. Have the distance of a capacitor hooked to a battery. Thou shalt apply thine reasoning and tell me, if I halve the distance between the plates of the capacitor, what happens to the charge, the voltage, the electric field, the energy density? What work do I do? Blah, 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 blah. Every term you could think of. Can you reason through? Hint, some are easier, some are harder. You can't just apply equations. You have to think about what the equations mean too, because sometimes multiple terms in the equations will be varying. This is one you'll want to do with each other. Make a list of all the electronic terms you know and think about, how does this affect that? How does that affect the other? What is in control here? What affects what, and what is affected by what? Give you maybe 7 minutes, then I'll start giving a couple and then giving you more time. Yeah? Good luck and have fun. GLHF. Anything I'm missing? Q, V, C, E, U, the work I do. What else can I put in? Lola Q, there is no test charge. Force, the force. This isn't in the Google form, by the way. I don't want to grade 15 things. You out of here? Yeah, you got well, you got through most of the class. You brained hard on everything but the last. You got some of them great. Good, good, good. Yeah, make sure that what's inside your head is right. That's the hard part. Good. I don't want you to miss anything either. No, the variable Q charge, the variable V volts, the variable C capacitance, electric field, energy, work, force, Luke. Use the force. Is it what? May the force be with you. Ciao.
How are your Thursdays? Particularly, I get out of a lecture at 10:15.
I have to look. Thing is, Thursday is my one early day that I don't have later stuff and I'd like to go home. Thing is, maybe not all the time, maybe every once in a while, like every other week. Then once upon a time I can have a nap. And the other time I can work with you. You're worth it. Just, I do want naps occasionally. What else? Oh, the mornings, I'm always teaching at the high school, 8:15 to 9:40. So I can't do mornings. Hold on, let me look. I can't remember anything. Let me look. Okay, one more minute, then I'm going to start giving tips, tricks, how to think about it. Oh, God. Got 9:40 to 10:30. Everything else is back to back with only 15-minute breaks. There is after lab never takes the full 2 hours and whatever. We could squeeze it in before the 3 o'clock class, but that's dodgy. Any chance you have Monday or Tuesday at all? Any chance you got before the lab?
Yeah.
Yeah? You get out of lecture at 10:15. I finish a Morse code session at 10:30. We could do 10:30 to like, I don't want to do at 12, 10, 10. God damn it. No, 15. I just need to make sure I have time to walk over and open the door. Okay, so what is that? 10:30 to 11:45? No, we could do that every week. Yeah, that's not cutting into my nap time. My precious once a week nap. My precious. Okay, come to my office, okay? Okay. Well, you don't have to do every week. If you want to do every week, we can do every week. Okay, K-Money. It is harder for me to think of Kendra. Kendra, right? Kendra? Than K-Money. Yeah, because you put it on the form, it's funny. You're funny, K-Money. Okay, here we go. Already set, let's think about it. The first thing I think you should think is, hey, what am I changing? I'm changing geometry. I'm changing geometry. That's something straightforward. I know how geometry affects, bang, capacitance. Capacitance is what? A epsilon over D? If I halve the downstairs of a fraction, what have I done to the fraction? If the downstairs gets half as big, what happens to the fraction? Ups by dose. Doubles. How can I interpret that? How can I make some sense of that, think about it, intuit that? Well, Remember my silly, silly story about the dorms on wheels, right? When you bring the dorms closer to each other, it's easier to bilk the students for all their money because they're busy making goo-goo faces at each other. Capacitance goes up as distance between them goes down. The charges are more closer to canceling out when the pluses are almost on top of the minuses. Halving the distance between them boosts the capacitance. Okay, so that's one thing. Another thing that I think you should think about is that voltage stays the same. You're connected to a battery, baby. What's true about components connected in parallel, connected directly to a battery? Voltage same. That's what a battery does. Okay, now that may cause you to need to reevaluate some of these. I'll give another minute for you to think through the consequences of your actions, the consequences of these hints. What you working on? Can I call you J Money? She's K Money? No, that's terrible. I'm sorry. I regret my decision. What? Jamie? You prefer Jamie or Jameson? Okay. I'll call you either's fine then. What you working on? Huh? Good. Okay, time's up to think. I think. CV immediately. Knee-jerk reaction. Q. Q equals CV. If C stays the same and V doubles, Q doubles. Why does this happen? Why does Q double? You're bringing positives and negatives closer together. Their electrical desire to separate is reduced. The battery can flow some more charge on. A current can flow onto the plates. Again, why is the voltage the same? Voltage, you're connected to a battery. The battery keeps a constant pressure no matter what. That's his goal. That's his aim. That's his purpose. Now I've got Q, V, and C. Go buy some crap. No, sorry. That's only if I have QVC. What can I find from that? What do I know based on that? I also have D. I know something about D. That's a given. D halves. Do I know how how D, Q, C, V are related? Well, isn't there a term about V and D? Are V and D related? That's true. QD over A epsilon naught. QD over A epsilon naught. Wait, what? V. What? V equals, but we already reasoned about voltage. Okay, I think V and D are related to E. How are V, E, and D related? No, you don't need a Q. That's a true statement, but that's not how D, V, and E are related. D and V affect E. No, directly. Directly. VED, volts equals newtons per coulomb times meters. If D halves and V stays the same, electric field, well, volts per meter. If volts per, wait, hold on a second. Yes, I was thinking of the previous example. Yes. In the example I gave the 3 o'clock class, electric field stays the same. Here, we are halving the distance and same voltage. Another way of measuring newtons per coulomb electric field is volts per meter. If volts stay the same and meters halve, electric field doubles. Okay, we can also, that's the way I was thinking about it in terms of V, E, and D. You need to be able to connect those pieces. David was thinking in terms of charge. How is charge connected to E field in a capacitor? Q over A epsilon, and those don't change if Q doubles, A doubles, E doubles. How are these terms related to total energy stored in the capacitor? 1/2 QV, Q doubles, V stays the same, U doubles. That's a fair amount. Look at that. That's 6 terms. Turn to each other and discuss why. Intuitive and equation based on equations. Right. For which? Sorry, I derped. QV. Q doubles. V stays the same. No, the 1/2 is the same in either case. 1/2 of 2 times 1 and 1/2 of 1 times 1 is still double. So in terms of its original definition that is always true is charge per volt. Q over, oh, for God's sake, Q over V. But for a parallel plate capacitor, A epsilon over D. Okay, we're about out of time. The work I do, what I would say is it's negative. Why? Intuitively. How much do I have to do to push a positive to a negative? You can release energy that way. Yeah? How much energy could you release? You need the force. Wait, what is the force? Hold on, we can do the force. One of the charges is Q. One of the electric fields that pulls on that charge is doubling, is some QE. If Q is doubling and E is doubling, I think the force is, oh, never mind. Whatever. The force I exert is positive. No, sorry. What I have to exert to get them to slide together is I don't need to exert a positive force. I can exert a negative force and still have it do work. My force to force them together doesn't have to be pushing them together. I could be exerting a force in the opposite direction and letting them slowly come together to get that negative work. Now I challenge y'all. Yes, I know this hurts. That's the feeling of your brain growing. Productive struggle is a good thing for mental development. Okay, so here's my challenge. Disconnect it from a battery and all these things change. Check your answers against what I put. I put most of those answers in the 3 o'clock class. That's in the lecture notes. That's an exercise. Don't do it now. But if you think about why this affects that, affects the other, maybe I could say at least one of these will be on the test. Hint, hint. I mean, that's always a true statement. Maybe, at least, anyway. Okay, I love each and every one of you. You are all awesome people. We are out of time. I will see you on review day Monday. Bye. Have a good break. Brandon, if I pull the capacitor plates apart, what do you mean create negative? No, I can let the capacitor plates go together. I don't have to exert a positive force pushing them. I can pull on them and they will still come together. What force do I have to do to get that to pull together? A negative force will allow that to happen. Thank you, Brandon. Email me, by the way. I've got a question for you.